Okay, so yesterday we were talking about periodic trends. We were talking about different trends that you can see and use on the periodic table. Yesterday we talked about atomic size, atomic radius. And atomic radius is how big the atom is. Okay, from the center of the nucleus to the outermost electron. That is the atomic radius. And we know that as you go down the column, down the group, they get larger and larger and larger. Why do they get bigger? Do you remember why? You get more energy levels, more shells. So every time this has got one energy level, two energy levels, 3, 4, 5, all the way down, correct? So every time you add an energy level to it, obviously it's going to get bigger. If you've ever done a box and a box and a box as a gag gift, you know, you buy them a little present and then you put them in all these different boxes and you wrap them each time. The final box has to be bigger than all the previous boxes, right? So it's kind of the same thing. So it makes sense why they are getting larger. So as you go down, the energy levels increase. Are you good? Okay. Now, and we did the demonstration of the alkaline metals. Now, as you go left to right, they get smaller. Why do you think they get smaller? Look at this atomic radius. Big down to small. Why do these guys start off small and they get big? We know that reason. But why do they get smaller as they go across? Why do you think? Well, I'll tell you. Okay? It's because of something called shielding electrons. Shielding electrons are the inner electrons. Okay? They're the electrons like the core electrons. And let me show you this. Okay. So, if you look over here. So if I have, let's say, we'll do sodium. Sodium has 11 protons, right? We're all, right? Got that? Draw a board diagram. It's going to be 2 electrons, then 8, then 1. So far, so good. Yeah. Well, basically what it is, we know the protons are very attracted to the electrons, right? And they're reaching out and trying to pull in on them. These protons want these electrons as close to them as they possibly can. That's what they want. So, as these electrons try to pull them in, they go through 2, then 8 to get to the outermost shell. Well, you've got 11 protons and right here 10 electrons. If this were a football game, it's almost like a man-on-man or offense or defense or play, whatever it is, right? It's almost a one-to-one blocking situation. The chance of them getting to this outermost electron are not very good. That's why these guys are a little bit larger. If you look at something like sulfur, sulfur has 16 protons, 2, 8, and 6, right? Now we've got 16 protons coming up against 10 electrons. Which is a better defense? Sodium or sulfur? Or which one, I don't know my defense from my offense, sorry. But which one has better coverage? Sodium or sulfur? Sodium. Because sodium is going to be it's a 10 to 11 matchup. Over here, it's a 16 to 10. So what's the likelihood of these 6 being affected out of here? Much greater. So those 16 are going to take out those 10, go past those 10s very quickly. Does that make sense? Because I have 10 shielding electrons here and 10 shielding electrons here. But I've got the protons are different. So that's why these guys reach out, grab these guys in the atom, it's smaller. Does that make sense? Yes or no? Okay, good. So they're called shielding electrons. And this was my first attempt at trying to show the offense and defense or something like that. And then there's a sulfur. I think mine on the board's a little better actually now. Yes, sir?
How would you do it against the gas like argon?
Well, argon has 8 electrons in its outermost shell. It's the exact same thing. They also shrink as well. They get smaller all the way across. Because argon has 18 protons, and it's got 2, 8, and then 8. So it's the same thing. So if I had even 18 electrons here, did I move that? And I'd have 8 out there, still it'd be 18 up against 10. Does that make sense?
Yeah.
Okay. Good. Okay. So, again, here's a shielding electrons. For lithium, there's 2. And then for carbon, there's also 2. And for neon, there's 2. But as you go across, you get your protons go up in number, and therefore it gets smaller and smaller and smaller. And that's why it looks like this. Let me see. That's why as you go across, they get smaller. That's the trend. The trend is they get smaller. Yes? So far, so good. Okay, so now we're going to do a worksheet on atomic radius. And let's see if I can just pause this a minute. Okay, there we go. It is recording. So, it is. Yes, it is. Okay, so now let's talk about valence electrons. We've kind of mentioned valence electrons a few times. Valence electrons are those electrons in the outermost shell. That is what valence electrons are. They're the electrons in that outermost energy level or outermost shell. Okay? Valence electrons will determine the chemical property for elements. The core electrons do nothing. Well, for the most part, nothing. But we need to understand the valence electrons because they're the ones that help with bonding, help with the chemical properties, and determine what's going to happen in a reaction. These are those electrons in the highest energy level, and they are related to the group numbers. They are related to the group numbers. Okay? So boron has 5 protons. How many electrons will it have? 5. Why would it be 3? Okay, well don't we know that the number of protons equals the number of electrons in a neutral atom? Okay, so the number of protons equals the number of electrons in a neutral atom. So there are 5 electrons. 1, 2, 3, 4, 5. These 3 are my valence electrons. They're in the outermost shell, right? So there are 3 valence electrons. 1, 2, and 3. So far, so good. Right, Sebastian? Yes? Okay. So, using the electron configuration for chlorine, how many valence electrons does chlorine have in its outermost shell right here? 7. And if we write it with electron configuration, this is my outermost shell. The 3rd energy level is the highest energy level. 2 plus 5, there's 7 valence electrons. Does that make sense? So either if you write it in Bohr diagrams or the electron configurations, you still get the same numbers. Yes, sir?
You just take the last 2?
Well, you take the highest energy level. 1st energy level, 2nd energy level, 3rd energy level. So the 3rd energy level is the highest energy level. Okay? So that's the outermost energy level. Now, if we look at this one, this is germanium. Now, what's my outermost energy level?
14.
What was it?
14.
14. Okay, I can see how you'd think that. I got the first energy level, second, third, and fourth. What's my outermost energy level? The fourth. So what I do is the fourth level is my outermost one. So I only consider the 4s2 and the 4p2. The 3d, even though it has a higher energy, is not in the higher energy level. Does that make sense? So you take the outermost energy level. We're not looking at the highest amount of energy, just the outermost energy level. Okay? Does that make sense? Yeah. Okay, good. And this shows you all the different energy, the electrons. All these have one valence electron. 1, 1, 1. These all have two valence electrons. These all have 3, 4, 5, 6, 7, and 8. And let's look to see what groups they're in. These are in group 1. Group 1 all has one valence electron. Group 2 all have two valence electrons. We skip the transitions. They're not very much fun. Group 13. Remember, it used to be called 3A back in the day. Now it's group 13. Group 13 has 3 valence electrons. Group 14, Griffin, has 4 valence electrons. Group 15 has 5. Like that. Does it make sense? So if you look at them, sorry, let me get through these real quick. So the valence electrons on the table. The first group has 1 valence electron. I would probably write this down on your blank periodic table that I gave you so you can kind of go back and refer to it. That's what I would do personally. So I'd write valence electrons. So group 1 has 1 valence electron. Group 2 has 2 valence electrons. We skip transitions. They're kind of wonky and we'll get to them later. So far, so good. Group 13 has 3 valence electrons. Group 14 has 4. Group 15 has 5. See the trend? Group 16 has 6. Group 17 has 7. Group 18 has 8. Does that make sense? It's pretty straightforward. I will also ask you this on the test. Yes, sir?
What about 3D? Or no, just like the D block.
We skip those.
They don't have any valence?
They do, but remember, we look at the higher energy level. We look at the higher level that they're in. So we have 4s2, 3d something, or 40, no. 4s2, 4p3. 3d's in there, but we're still in the 4th energy level. So we don't worry about these. Now, if I'm talking about this element here, like iron, they rearrange their electrons to do strange things. And we'll talk about that a little bit later. Okay? So far, so good, yes? Now, I would give you a worksheet on valence electrons, but I don't think we necessarily need it. If I walk over here and say, okay, let's see what we have. So, Lynn, how many valence electrons does gallium have? 3. Let's see, Sarah, how many valence electrons does polonium have? 6. Let's see, Cole, how many does cesium have? 1. It's pretty straightforward, isn't it? So I thought doing a worksheet on it might just be a little not necessary. Are we okay with valence electrons? Thumbs up? Yep. Okay, good. Okay, so now we're going to talk about electron dot diagrams. Electron dot diagrams are a way of showing how many valence electrons there are using a symbol. Okay? So for example, chlorine, here's my symbol, has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. You just put 7 dots around them. That's all you do. For magnesium, it has 2 valence electrons, you put 2 dots. Yes, sir? It really doesn't matter where the dots go, but what matters is you have 2 dots on each side. Atoms can hold up to 8 valence electrons. So if you put chlorine like this and went 1, 2, 3, 4, 5, 6, 7, that would be incorrect. You need to have 2 on one side, like a little box, kind of like the Vogue thing, and then 2. But it doesn't matter. I could have put the single electron over here. Does that make sense? Yes? Okay, yeah. Electron dots are pretty fun. They're very simple. But the reason we use electron dots when we talk about them is because when we get to bonding, you use the electron dots to help you bond, to show you where these bonds are going to happen. So that's why. We all good so far? Okay, now we're on to all these electron dots. They all have 1, they all have 2, 3 for each group. Does that make sense? Okay. Ions. Ions, yeah. Ions are charged particles. If something is an ion, it's charged. So it's an atom or a group of atoms that have a charge on it. Okay? So an ion is an atom or a group of atoms that has a charge on it. The charge can be both positive, or it can be either positive or negative. In an ion, protons do not equal electrons. The atom is no longer neutral. The protons do not equal electrons in an ion. In a neutral atom, like you see on the periodic table, then that's neutral. The protons equal electrons. But in an ion, they do not. Okay? And if they become a positive ion, we call them cations. No. No. Cations are plusy cats. Positive pluses. Get it? Cations are plusy cats. And they are not cations. In the video you're going to watch in a second, she says cation. Cation. It's a cation, not a cation. And never ever tell Mr. Reeve it's a cation. You want to see him like lose his outer layer of skin. That's time you learned about cations today. So cations are positively charged ions. Okay? Anions, I came up with a negative ion. An anion is a negative ion. So cations are positive, anions are negative. Okay? Yes? So far so good? Okay. Oh no, I'm hit. I've lost an electron. Are you sure? I'm positive. Because when you lose electrons, you become more positive. When you gain electrons, you become more negative. Get it? Right, you lost an electron. I'm positive. Anyway, so a little science humor there. Now, a quick video. So the outermost shell. She's from Canada or Minnesota, so you'll hear a bolt and things like this. So, just so you know, that's coming.
In this lesson, we will learn about what ions are and how they are formed. When an atom gains or loses electrons, they develop a charge. Recall that electrons are negatively charged, so the gain or loss of electrons will create a charge. These charged particles are called ions. When an atom loses electrons, they become positively charged. Positively charged ions are called cations. An easy way to remember this is to recall that cats have paws.
At this time,
When an atom gains electrons, they become negatively charged. Negatively charged ions are called anions. Let's look at sodium as an example. Its electronic structure is 2.
Real quick, guys.
And bring your scheduling materials.
If you go to scheduling, you're responsible for making up any material by watching the video. Also, when you come back, make sure you get all the papers you missed. Okay?
8 and 1. It has 1 electron in its valence or outermost shell. When sodium loses this valence electron, it becomes a positively charged sodium ion. This charge is written as a superscript when writing the symbol. When drawing the electronic structure, enclose it in square brackets and write the charge on the top right-hand corner. Now, let's look at oxygen as another example. Its electronic structure is 2 and 6. Therefore, there are 6 electrons in its valence shell. Oxygen gains 2 electrons to form a negatively charged oxide ion. Remember to include the charge when writing the symbol and when drawing the electronic structure.
We don't put the brackets around it.
If we look at the electronic structure of these 2 ions, we will see that they have a complete outer shell. We will also see that they have the same electronic structure as that of a noble gas. The sodium ion and the oxide ion have the same electronic structure as a neon atom. How are you feeling about ions? Are you ready to form ions on your own?
You okay?
Let's try. Please pause the lesson and draw the electronic structure of a calcium ion and a chloride ion.
So draw me a board diagram for a calcium ion and a chlorine ion. I'll walk around and look at them. Draw a board diagram for each of those. Make sure you use that. Where's your periodic table? Make sure to keep it out, okay? Thank you. Where's your periodic table I gave you? Guys, make sure everyone has their periodic tables out so you can use them. Most important instrument any scientist will ever have. Okay, so calcium. Okay, so you have calcium is 20, right?
But
So-
it's,
well,
oh, wait.
that's plus 2.
so
Plus
you said-
means you lose them.
Yeah,
So you're going to lose that whole outer shell.
yeah.
Okay?
So I did have it right.
Right. Okay, good. Okay, to become a plus 2 though, it's going to lose that whole outermost shell. Because that's calcium. And they want you to draw the calcium ion. So for a calcium ion, it's going to lose these 2 electrons to become calcium plus 2.
So.
See, you have 18 electrons
Oh,
here,
yeah, 'cause
20
they
protons.
would've been neutral.
Right, perfect.
So if it's just like there's no number up there, then it would be a 1 like in math with how like you would have
Yes,
x plus 4,
yes.
so x would just be 1.
Yes, perfect. Okay, let's get moving forward and see if we can figure this out. Here we go. So, check your answers with the video, please.
The electronic structure of calcium is 2, 8, 8, 2. It loses 2 valence electrons to form a calcium 2 plus ion. The electronic structure of chlorine is 2, 8, and 7. It gains an electron to form a chloride ion. These 2 ions have the same electronic structure as an argon atom. Did you get the structures right? And
Did
did
you?
remember
You guys got 'em
to
right.
specify the charges?
Yay!
What do sodium and magnesium have in common? They are both metals, and metals lose their valence electrons to form cations. Group 1 metals, such as sodium, have one valence electron, and they lose this electron to form ions with a +1 charge. Group 2 metals, such as magnesium, have two valence electrons, and they lose these electrons to form ions with a 2+ charge. Oxygen and fluorine are both nonmetals. Nonmetals tend to gain electrons to form anions. Oxygen is in group 6 and has 6 valence electrons. It gains 2 electrons to form an ion with a -2 charge.
Oop, my bad. Well, real quick. Why, it's almost the end, why would oxygen gain 2 electrons rather than giving up 6? That's one thing I was trying to stop it. So it was saying that, it kept saying, okay, so you've got oxygen with +8 and 2, 6. Now 2 is also a complete outmost energy level as well. You have to understand this. Atoms don't want to be neutral. They're all neutral up on the periodic table, right? That's not their thing. They don't want to be neutral. They want to be stable. They want to be stable like the noble gases are stable. Okay? The noble gases are the most stable elements on the periodic table. Okay? So all other atoms want to pose to look like the noble gases. So they're going to lose or gain electrons to get the same electron configuration as a noble gas. Okay? So here's oxygen with 8 protons and 8 electrons. Trent, please. Okay. So every time it loses or gains an electron, it requires a certain amount of energy. And atoms are lazy. They only want to expend as much energy as they possibly can. So are they going to give up 6 electrons, 6 times the energy, or 2 times the energy by picking up 2 electrons? They're going to pick up 2. It's easier to pick up 2. So that's why they gain 2 electrons. And now we have 10 electrons, 8 protons, so oxygen's a -2. Does that make sense? And that's why if you have calcium with 2, 8, 8, and 2, is it going to pick up 6 electrons or get rid of those 2? It's going to get rid of the 2. It's easier for it to get rid of the 2 than to pick up 6 more. So that's why they do what they do. That's why they lose or gain them. They're trying to get the electron configuration of a noble gas. And we'll see that when we come on up here. Okay? So, then you have, what element is this?
Magnesium.
Thank you, magnesium. So it's got 12 protons. How many electrons will it have? 12, because it's neutral originally. So 1, that's the magnesium atom. They all came up one by one. I got tired of it. So this has 12 protons, 12 electrons. It's neutral, right? Does it want to be neutral? No. It wants to be positive. It wants to look like a noble gas. So it loses those 2 electrons. See that? Off they go. Now it has 12 protons still. The number of protons cannot change because that's what makes it magnesium. But the electrons can. So now I've got 10 electrons. It has a +2 charge. What noble gas has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons? Neon. Magnesium now has the electron configuration of neon. It looks like neon from the outside, but is it really neon?
No.
No, it's a poser. It's just magnesium wearing the coat of neon. Okay? So now it's a magnesium plus 2 ion. Does that make sense?
Yeah.
Okay? Sodium atom. 1s2, 2s2, 2p6, 3s1. It loses that one electron. It loses the entire shell, actually. The entire shell goes away. As you can see here, here's my outermost electron. They give it up. And now look at it. It also looks like neon, doesn't it?
Yeah.
Okay? So, now, on that same blank periodic table, I'm going to put up here the charges for each of the atoms, or each of the columns. So everyone in group 1 will have a +1 charge. If you look on the periodic table I gave you, in the upper right-hand corner, you will see a 1, 1, 1, 1 going down each block. Do you see that? That's your +1. You should always have a plus or a minus in front of these numbers. However, some of the numbers had like 6 charges it can take. I couldn't put a plus in there. So I figured if they're positive, I just left them without a sign. I could have done that for some, but not for the others, and I couldn't have had that kind of chaos on my periodic table. So everyone in the first column is a +1. Everyone in the second column is a +2. Do you see that on your periodic table that I gave you? They're all 2s going down. Do you see what I'm talking about? Okay. So if you look here, see how it's 2, 2, 2, 2, 2. Yeah?
I already saw it.
Oh, did you? Okay. Do you see how it's all?
Yeah, can I get for the nurse to get some?
Of course. Yeah. You see the 2s going down? Okay. We skip transition metals. Skip these guys. They have multiple different charges they can take. Oh, Logan still has the pass. Okay. Group 13 has a +3 charge. Now, what if you have 4 electrons in the outermost shell? Do you pick up 4 or do you lose 4? Either way. They go either way. So it's plus or minus 4. It all depends on what it's reacting with. And then we say group 15 is -3. It's going to gain 3 electrons. Group 16 is going to gain 2 electrons. Group 17 is going to gain 1 electron. And of course the noble gases don't need to gain any because they're noble. Does that make sense? Are we good with this? Now remember, if you look at this, remember our stair-step line? These are all metals. Metals all tend to gain electrons. Metals will tend to gain them. Non-metals that are on this side, look, negative, 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 they will tend to lose them. Okay? So remember this when we're doing other things. We'll use this in the next several chapters to come. Metals lose electrons, non-metals gain them. So far, so good. Yes? Any questions? Now, one last thing I want to talk to you about is isoelectronic. When these ions are formed, they have the same electron configuration as noble gases, don't they? Then the noble gas and that ion have the same electron configuration. They're called isoelectronic. Here's neons, electron configuration. Here's oxygens. These guys are isoelectronic. Here's fluorines. They're the exact same. They're isoelectronic. Here's sodiums. They're isoelectronic, which means sodium +1 is isoelectronic with oxygen -2. They all have the same electron configuration. Anything with the same electron configuration but are different atoms are isoelectronic. Does that make sense? Yes? You good? Okay. Whoop. And that is the end of those notes.